All right, let's do the second part of 14.2, 14.2b, as in to be or not to be. That is the question. So here is 14.2b, entitled Tangent Lines to Circles. Okay, a lot of theorems in here. Good stuff. Not all that difficult to prove. A lot of triangles and perpendicular bisector theorem and so forth used here. But first theorem says the perpendicular from the center of a circle to a chord bisects the chord. Okay. And we'll just do some informal proofs, but I really want you to try and figure this out on your own. So go ahead, pause it. Again, hint will be to draw in radii and see what you can do from there. All right, so we're going to go through this one now. So the informal proof here is HL, then CPCTC, right? Because if we draw in radii, what do we know about radii? They are all congruent, right? So we know that's congruent to that, and we know this leg is congruent to itself. So then we have HL and CPCTC, which means that this and this are congruent, which means this bisects the chord. Okay, lovely. Next one, the segment from the center of a circle to the midpoint of a chord, which is not a diameter, is perpendicular to the chord. Okay, so now go ahead and try and prove it. I almost said it. Go ahead and prove it. And then I'll uncover. Okay, so I'm back, and hopefully you drew your triangles in and you marked up what was congruent, and you saw that you had SSS and then CPCTC, and then you can say that right angles are congruents, or I guess a linear pair that's congruent angles is they've got to be right angles, right? Okay. All right, next one. In the plane of a circle, the perpendicular bisector of a chord passes through the center of the circle. All right, so yeah. All right, so again, we're not going to go through that one, but in a plane of a circle, the perpendicular bisector of a chord, right, passes through the center of the circle. Okay. All righty, onward and upward we go. Corollary, no circle contains 3 different collinear points. Why is that? Why no 3 different collinear points? Yeah, it's a circle, right? How in the world is that possible, right? How could you have, if the most that a line can intersect, the most points a line can intersect a circle in is 2. How could you have 3 that are collinear? Impossible. Okay. All right, congruent circles. What do you think congruent circles have? Yes, the same. Whoa. Sorry about that. Yeah, they have the same radii, right? Or same length radii. Congruent radii. Awesome. Yeah, same shape, same size. Okay. All right, here's a good theorem. In the same circle, or congruent circles, chords equidistant from the center of the circle are congruent. Yeah, right? So let's do the proof of this. So here we have congruent circles, right? Yeah, if we have, if the chords are equidistant, that means this and this are congruent. We already know we got perpendicular. And what do we know? If they're congruent or the same circle, what do we know about their radii? They're congruent too. All right, so chords equidistant of the circle, from the center are going to be congruent, incongruent, or the same circle. Okay, next theorem. In the same circle or congruent circles, any 2 congruent chords are, yeah, this is just the reverse, right? Equidistant from the center, okay? And you could do that by SSS, right? If we know that the chords are congruent, you can drop that and basically go through the same thing. I don't think I have a diagram. Oh, I just was going to use that for, okay. All right, then we have the line circle theorem. It says if a line and a circle are coplanar and the line intersects the interior of the circle, then it intersects the circle in 2 and only 2 points. Again, what does that relate to? Yeah, no circle contains 3 different collinear points. Okay, so these all kind of interrelate and they all pretty much make complete sense. Okay, so let's practice. And again, try these on your own, really dive into them, and then obviously I'll have the explanation for you. Okay, find the distance from the center of a circle to chord AB if AB equals 8 and the radius is 12. So draw that up, right? So the distance from the center of a circle to chord AB if AB is 8 and the radius is 12. All right, so here we go. So we had our chord is 8, right? We know that if we can draw this in, right, and it's going to split it into 4 and 4, and we're going to have a perpendicular bisector. We have 12, right? So what is the distance? Well, it's the length of this segment x, right? So x squared plus 4 squared is going to equal 12 squared. And what's that? 144 minus 16, 128, and then that is 64 times 2, so 8 root 2. Okay, yay. All right, try this one. In circle P, the diameter KN is 16. I'll mark this one up with you. Okay, so this whole thing is 16. And chord MQ is 10. So this whole thing is 10. Find the distance from the center of the circle to chord MQ. So in other words, we're trying to find this, and we know this is perpendicular because that's how we measure the distance from one thing to another. It's the shortest, right? Okay, awesome. Go for it. All right, so I'm back, and basically the way we could set this up is we know that this is 5, right? And we know that 5 squared plus x squared equals 8 squared, right? And therefore, x squared is going to equal 64 minus 25, which is root 39, okay? So you had to set up, what triangle did you set up? What triangle did you set up, right? If we know that Kn is 16, then we have, this is 8, right? Okay. And, wait a minute. This is 8. Why am I blanking on this all of a sudden here? We're trying to find that, right? So that's got to be part of our deal. And, oh, yeah, because if, that's it, silly me. If this is 8, that's a what? A radius. So guess what? That distance right there is also 8, right? And this distance here is 5. Oh, silly me, forgetting that for a second. Okay, good. Sorry about that. See, no one's perfect. It's all good. Okay, try this one. In a circle, a chord 6 centimeters long is parallel to a tangent and bisects a radius drawn to the point of tangency. Okay, so think about what this is going to look like, right? We have our circle. We have a chord that's parallel to a tangent. All right. And it bisects a radius drawn to the point of tangency. So your drawing should look like this, right? It says it bisects the radius drawn to the point of tangency, which is right there, right? So we know that this segment and this segment are equal. We know that the chord is 6. We know that this is going to be a perpendicular bisector, so that's 3. And I know that if this is x as a radius, this whole thing is x, so this can be set up as half x. And then it's just doing the math. So go ahead and do that. And here it is. So if I square 1/2 x, I get 1/4 x squared plus the other square of the other leg 9 is equal to x squared. And if I, looks like I subtracted 1/4 x squared from both sides, and I just kind of flipped the sides. And then I multiplied both sides by 4/3. Those would cancel. The 4/3 and the 3/4 would cancel. And then 3 and 9 become a 1 and a 3. 3 times 4 is 12. Square root of both. Root 4, root 3, 2 root 3. Okay, awesome. And now, this is one of the constructions that you're going to be working on. So how to find the center of a circle. One, construct a tangent, okay? You can just do what? You can literally just draw a line that intersects that circle in one point, right? Construct a perpendicular to the tangent at the point of tangency, so we know how to do that. And then if you repeat those 2 steps with another tangent, and then you connect those 2, right? Perpendiculars, right? They have to do what? They're going to go through the center of the circle. So wherever they intersect, that's going to be the center of the circle, because that would be the only places they intersect, or the only place they would intersect. Okay, and that does it for 14-2B, or not to be. That is the question. Come see me if you have any questions. Happy to help.